All right, talking more about functions here. We're going to keep running with these example formula-given functions that we were supplied with previously. F of x equals x to the fifth. G of x equals 7x. So we saw sort of like the classic, arithmetic combinations of functions like f plus g of x and so forth in our last video. What I wanted to pick up on this one was this maybe new to you, symbol to represent putting functions together. This little, open circle, looks like fog of x if you think of it as an O. And every now and again, math people will kind of, refer to it as that as a joke. But so the catch is that's something that we call the composition of two functions. So there's a blank sitting underneath that on the notes file. You can fill it in with composition, or we're composing, f with g, that sort of thing. And so now here's what that ends up looking like. So it's kind of like we feed the one on the inside, of this thing, g of x, we feed it into x. So we take the g of x formula and it's going to go into that guy. So f of g of x, waiting for the camera to refocus because it's gotten a little blurry on me. Come on. If you don't do this in a few seconds, I'm going to press pause until you sort your mess out. So, technical difficulties. Technology's great when it works. Anyway. So the idea here is we're going to take the formula for g of x and sort of feed it into f of x. So if you break this down, it's going to look kind of like, well, what's our formula for g of x? It's 7x. So we take that guy, and now anywhere we see an x in this formula, we're going to replace it with the stuff in these parentheses. That's 7x. So we end up with 7x, and the whole thing is raised to the fifth power. So yeah, that's kind of an important distinction there. Our properties of exponents say each of those things gets raised to the fifth, so you'd have 7 to the fifth times x to the fifth. And as it turns out, 7 raised to the fifth power is 16,807. So you have 16,807 x to the fifth. That coefficient just rolls off the tongue. So that's an idea of composition in action. So you kind of like do what G says first, and then do F to whatever you get out of that. So by the same token, the bottom of the page here, we've got the composition sort of reversed. Instead of F of G, as you read it, or instead of fog, and now we have golf, G of F of X. So we repeat the process, but now the guy on the inside is different. We feed into G the formula for f of x, which we said is x to the fifth. And so everywhere we see an x in this formula, it doesn't affect the 7, but instead of this x, we're going to have this guy in its place. So 7x to the fifth with no fancy, applying a power to the 7 in that instance. So those two formulas end up pretty radically different from each other. So we sometimes get kind of spoiled with our math operations because like addition commutes. 3 plus 2 and 2 plus 3 are both 5. 5 times 7 and 7 times 5 both give you 35. Composition, it doesn't work that way. I mean, it comes back to sort of the real world, often doesn't commute. You can't just exchange the order of any two actions that you might end up taking. So you do need to be careful about the order here. So keep that in mind. All right. So there's a few more examples here. I'm going to leave those for you to play around with. They just sort of try to hammer home the this connection between composition and the product functions. You see f of f on the next page versus f times f. And it gives you a chance sort of to play around with properties of exponents. I said in the last video, you can look up resources for how to handle properties of exponents. I wanted to look at the other examples in this section, before we leave 1.2 behind. All right. So in the more examples, I promise there's not always a more examples, but it's sort of funny that happens for both of these first couple of sections, right? So the next couple of examples, we're given like a table of x and y values. We're told, connecting those x and y values, that means it's automatically a relation. We're relating x and y. But we want to know if the arrangement sets up y as a function of x. So I'm going to write this first guy out and then we'll take a look at it, okay? So we have 0, 1, 2, 3. We have 1 at the end, maybe 3, 2, 8, 6, 4, and 5. All right, so there's our table of x and y values. All right, so it says, is it a function? If it is, identify the domain and the range. So remember, the key thing that determines that y is a function of x is that we can't have the same x value point to multiple y's, right? So as it turns out, if none of your x values pop up in this list twice, you're home free. It's a function. Great. Shoot off some, as you say, fire up the confetti cannon. But this time around, we do have a pair of 1s, right? So these are really the only bits that we're interested in at the moment. And you look at it and you say, well, we can't have one x point to different y's. Last I checked, 2 and 5 aren't the same number. So, yeah, so we have one x value connected to 2 separate y's. Since that happens in this instance, that is not, in fact, a function of x. So not a function, or is sufficient there. All right, so that's one example. The next one, try to be a little more compact, but you got this in front of you, but it gives me something to point out when I'm trying to describe stuff. So this time around, we're actually clear on this being a function of x because we don't have a repeated x value. So technically, whatever I write as far as the y's go, doesn't actually matter. 8, 6, 4, 8. Now you might end up saying, well, wait a second, we have multiple y's. It's okay to have multiple x's pointing to the same y. Remember, if you go back to that picture from the previous video, we can have multiple arrows ending at the same spot. We can't have multiple arrows starting from the same point. So this is a function. So the domain, if we list it out like in set notation, like we would have in finite math, we just take those x values and kind of put them in a set of curly braces with some commas. Now for the range, we could just list all of the y values. The trick is we have 8 listed twice, and you may remember from Math 107, we don't repeat entries in a set representation like this. So I would just write it like so. I would only list 8 a single time and not have the redundancy. And if you wanted, you can put these like in ascending or descending order. And so they're just about there. If you move the flip those 3 guys in the back around, but it's not vitally important in that particular instance. So like WebAssign will recognize them in any order, and generally we don't care about how things are ordered inside set braces like that. All right, so one more example to take a look at. It's kind of an application thing, looking at financing a loan. So you're given another one of these table of values deals, but instead of x and y, now we have, it says t and r. T being like the time of whatever the time period you're refinancing some mortgage loan or something into, and then r represents the monthly payment, and it says r equals f of t. So r is a function of t here. So I'm not going to recopy the notes table this time. I don't need to point at it too explicitly. But so you got that chart. You can sort of replace the r with an f of t, right? Equals f of t or something at the top. And we're asked to do a couple of different things with this. It says we find f of 15. So remember that 15 is standing in place of the t. So we find t equals 15 in our little table. And then we look to see the r, or f of t value that goes with it. So f of 15 per the file we're given is 898.83. And then we're asked to write a sentence describing what this means. And the idea is, remember, t is the term of the loan, the lifetime of the loan. So for a 15-year loan, the f of t is the r. That's the monthly payment. So and I'll put a $sign on this guy. But yeah, That's kind of the interpretation in this instance. I don't know why I put a box around that. Technically the entire sentence is like the answer, but you get the idea. So by the same token, if you were dealing with a 5-year loan, your monthly payment is the mind-boggling $1,980.12 cents. It's the 12 cents that gets you, right? All right. So the last thing that comes up in this section that I want to take a look at, it says, is f of 5 plus 5 equal to f of 5 plus f of 5? Can we distribute the f across that addition in there? And you may think so. We've done some distributing already. Let's take a look. So, well, what if we did the addition first? Well, 5 plus 5, again, hopefully you don't need me to tell you, that's f of 10. So now we can look up 10 in our chart here, and when I look up 10 in the chart and find the R value that goes with it, that is 1161.09. So, all right, so that's that. Well, what if we worked out each f of 5 separately and then added them together? F of 5 plus f of 5. Well, you look up 5 for your t, the corresponding f of t, or R value, is 1980.12. So you have 1980.12 plus 1980.12. You add those together. When I did the arithmetic here, I got 3,960.24. So the question you would be asking at this point is this equal to this? So those two numbers look alike. I'm really hoping you're shaking your head at your computer monitor at this point, because yeah, those are not in fact equal. So, and as it turns out, it's really special case kind of stuff where you can actually do that with a function. The types of functions where that can happen, they're very few and far between. They don't generally come up in the course of our math of finance class. So yeah, don't distribute a function is kind of the moral of the story here. All right, so the good news is that section was substantially shorter than the one that came before it, right? We didn't have quite so many examples. I did cut a few, but I think you can tackle those. Of course, I'm willing to answer questions if if something comes up. So now we're going to zero in and look at a slightly more specific type of function next time.